what could that quantity possibly be? By this argument, we know that that quantity could not be the expectation value of, say, a locally defined operator, because that just doesn't have the right equilibrium properties. So we're looking for a property of a quantum mechanical theory that does not equilibrate for a very long period of time. Okay, so that was the paradox that Susskind pointed out. And in the same paper in which Susskind identified this paradox, he also proposed a resolution of the paradox, which is he proposed that the dual quantity to wormhole volume is the quantum circuit complexity of the CFT state. In other words, say the minimum number of 2-qubit gates, say, you would need to prepare the CFT state from some fixed and simple reference state. So this conjecture that the dual is circuit complexity is sometimes called the complexity equals volume conjecture. And there have been many kind of variants of this conjecture. You might have heard of complexity equals action or some other relatives. In this work, we won't be kind of distinguishing between those different variants of this. So we'll just call all of these conjectures complexity equals volume-like conjectures, but for us, they'll have very similar properties. Okay, so what's the intuition here that circuit complexity could be the dual? Well, Suskind's intuition went something like this. So let's say that we model our CFT state by an n-qubit state, where n is the entropy of the wormhole. And let U be the evolution of the CFT Hamiltonian for a scrambling time. Then the state of the CFT theory after time t, is just given by the normal time evolution of the theory. Like there's some initial state psi, and we just evolve this by the time-independent Hamiltonian, e to the minus iht. So the state that you get after, say, t scrambling epochs is something like u to the t times psi. So you're just repeating, in some sense, the same circuit over and over again. And Suskind's intuition was that the complexity of the state, e to the iht, relative to psi, is something that should grow linearly with time, because intuitively there shouldn't be any shortcuts to preparing the state. So saying that the complexity of e to the iht times psi relative to psi is roughly t is basically conjecturing that this particular way of preparing e to the iht psi, that is the way that you get, just by applying u many different times, it's conjecturing that this is kind of the optimal way of preparing the state, or say the optimal way up to some, kind of small corrections. Okay, so this was Suskind's intuition for proposing complexity equals volume, and it's because this complexity seems like it should have the same linear growth behavior. So as a result of this conjecture, there were a number of works which were trying to provide supporting evidence that this conjecture is correct. And these works kind of came from two different sides. So on the complexity side, there were a series of works by Aronson and Susskind and Brandau, Bodanowicz, and Balasubramanian et al. And what these works showed is they showed that the linear complexity growth of states of the form e to the iht times psi, that it's plausible that the complexity of those states grows linearly. Technically speaking, what these authors showed is they showed kind of necessary but not sufficient conditions for that to be the case. And because unconditionally proving this linear growth property is something that seems extremely difficult, this maybe is kind of the strongest sort of evidence one might be able to create in support of this conjecture. Now, on the other hand, from the gravity side, there were also works that were trying to argue that the behavior of the gravitational states that are dual to this time evolution also have the correct growth behavior. So in particular, a series of works considered some states which they called shock states, which are very small perturbations to the time evolution of the CFT state. So the CFT state begins in some reference state TFD, which is stands for the thermofield double state. I mean, the details of this won't actually matter much for our construction. But what the author said is they said, okay, let's consider states of the form where instead of just applying u many times to this initial state, let's say that we apply u many times, but along the way, we also perturb the evolution by applying a small number of local operators, let's say O1 to OL, in between these applications of the normal time evolution. So think of these as like kind of local perturbations to the circuit that you get for preparing these states. So the reason that these authors called these shock states is that in some sense, these local operators that you're applying the CFT apply an energy perturbation to the system and are kind of throwing energy into the wormhole. So throwing energy into wormhole, perturbs its volume in some way. On the other hand, on the quantum mechanical side, we can model these insertions of these local operators as the insertion of, say, 1 qubit gates into our time evolution. So instead of applying the same circuit u many times to our state, we say apply u and then apply a 1 qubit gate to one of the qubits of the state, and then apply u again and apply a different 1 qubit gate to the state, et cetera, et cetera. So these are like the normal time evolution, but with a small amount of perturbation. So what Stanford and Shankar showed in 2014 is that the changes to the wormhole's volume that are induced by inserting these local operators precisely matches the changes in the complexity of these states that one would intuitively guess by adding in these operator insertions. So this was one of the key bits of supporting evidence for complex equals volume, is that it seems to be having the correct behavior, not only on this one state given by normal time evolution, but also this conjecture also seems to be robust to adding some small perturbations of the system as well. Okay, so this is the conjecture and the evidence that has been provided to support it. And this conjecture, though, when you tell it to a computer scientist, at first glance, it might seem very counterintuitive, because it's conjecturing that complexity, circuit complexity, is dual to a physical quantity like wormhole volume. And to a complexity theorist, this might seem very odd. I'd say, here be dragons. Just because computer scientists have been studying this circuit complexity quantity for a long time and know that it has some very counterintuitive properties that one might not expect physical properties to have. So what is this computer science discomfort? Is that there seems to be some sort of type mismatch between complexity and volume if you're trying to equate these. So more formally, the computer science intuition is that circuit complexity of, say, a quantum state or a classical function is something that should be extremely difficult to feel or estimate. This is something that's been well studied in the context of classical circuit complexity. This goes back to works in the 90s, like the natural proofs barrier of Razvarov and Rudich, though there are even precursors before that. So complexity feels like a quantity that's very difficult to feel or measure in a physical theory. It's something that's very difficult to estimate. On the other hand, the wormhole volume of an AdS wormhole sounds like a quantity that should be very easy to estimate. It's a quantity that sounds very physical, right? That there should be some way of measuring the wormhole volume given some, say, description of a metric of your AdS space. So you can see that this means, one might intuit that there's kind of a tight mismatch here, that the, conjecturing complex equals volume sounds like it's equating a quantity that's difficult to estimate with a quantity that's easy to estimate, which seems very odd. Okay, but it turns out that formalizing this computer science discomfort with complex equals volume is actually surprisingly challenging. The main reason is that only a very special subset of states are being considered in this complexity equals volume conjecture. So, the evidence for it that we have is really limited to, time evolution by the CFT Hamiltonian, as well as these shock states, kind of small perturbations thereof. So, maybe the complexity of these shock states is somehow easier to estimate than that for general states. If so, that would invalidate this kind of point one, that complexity should be difficult to feel or estimate. The second kind of subtlety is that it's not entirely clear that the wormhole volume is something that should be easy to estimate. It turns out that in classical GR, no single observer living in the AdS spacetime can personally estimate the volume of the wormhole. So one might wonder if this information is somehow inaccessible. So if the volume were something that were hard to estimate, that's also something that would kind of relieve this tension between this tight mismatch between in the duality. So in our work, we set out to ask, can these objections or this discomfort be realized in the context of AdS CFT? And if so, what would it mean for the correspondence? And this is precisely what we did in our work. In particular, we showed that one can actually formalize this discomfort in this theory. In particular, our first result is to show that the shock states which arise in this wormhole growth paradox are something that are called computationally pseudorandom. This is kind of an analogy of a T-design. I'll give a more concrete definition later on. But the basic idea here is that what we show is that if you are given a CFT state with an unknown shock pattern, like an unknown pattern of local operator insertions, it would be extraordinarily difficult to distinguish that state from a hard random state. And what this means is that the complexity of these shock states, or more generally, the length of time evolution of them, is a quantity that is not feelable. So it's a quantity that should be exponentially difficult to estimate, even with a quantum computer. So in other words, this is kind of formalizing this idea that the complexity of even this tiny subset of states is something that's extremely difficult to estimate, therefore formalizing this kind of computer science discomfort with this conjecture. So I'm going to describe shortly as the implications of this result, but since this is actually the core of our work, what I'm first going to do is provide some kind of high-level arguments for why these shock states are computationally pseudo-random, and then we'll get into the interpretation of this result and what it means for AdS CFT next. So in order to do this, it's going to be helpful to provide a very brief review of some cryptographic primitives from computer science. And so I'm going to give a very brief introduction to these cryptographic tools from a quantum gravity perspective. And we'll then, in just a few slides, we'll see how this is almost directly connected to the shock states that are being considered in the context of AdS CFT. Okay, so the cryptographic story goes back to a really fundamental question, which is, how should one encrypt data over the internet? So let's say that you have some message X, it's an n-bit string, and let's say you have another n-bit string, which is a secret key. So a natural question to ask is, how should I encrypt my message with my secret key in order to send it as plain text over the internet? In which someone could potentially read my encrypted message, but I want to protect my encrypted message from eavesdropping adversaries. Well, the first attempt that everyone learns in Introduction to Cryptography class is to use a one-time pad. So consider encrypting your message X by simply XORing in the secret key K into it. Now, the nice thing about this encryption scheme is that it has perfect information theoretic security. So if you don't know anything about the secret key K, and K is chosen randomly, the encryption of X with K is itself just uniformly distributed. So you learn zero information about the message from viewing the encryption, right? This is almost the ideal sort of encryption that one could have. But the challenge with this one-time pad is that it only really makes sense to use the same secret key once. The reason is that if you use the same secret key to encrypt multiple messages, you end up leaking a huge amount of information about the messages you're sending. Like, for example, if you have messages X1 and X2 that you're sending that differ by just 1 bit, then their encodings in this scheme with the same key will also differ by just 1 bit, namely on the exact same bit x1 and x2 differ from. So there's a huge amount of information that's leaked from this encryption scheme, and this is why it's essentially not used in kind of modern modern internet encryption. So what's used instead, what's happening here is that this encryption is kind of way too structured. Like the relation between the encryption and the secret key in the message is kind of way too simple. And it would be nicer if our encryption scheme were somehow more scrambled or less structured, such that we could use the same key multiple times while still having security. And it's exactly that intuition that led to the design of what are called classical block ciphers. And these, the basic reason that classical block ciphers work is actually because of information scrambling. This exact notion that we've been talking about a lot in the context of quantum gravity. So the way that block ciphers work is they work something like this. So they say, let's pick some permutation sigma of n-bit strings that is really highly scrambling. So it will be a fixed permutation. It's something that will be publicly known, but it should be a permutation that mixes up strings quite a bit. And the way that we're going to encrypt our message X is we're going to take our message, apply sigma, then XOR in the secret key with this to our message. So apply the secret key to every bit of the message, then apply sigma again, then apply our secret key again, et cetera, et cetera. And we're just going to repeat this some large number of times. So what's the intuition here? Like, why is this a reasonable encryption scheme? Well, the basic intuition is that this encryption scheme is very easy to decrypt if you know the secret key K, right? Because sigma is public knowledge. If you get an encryption and you want to decode it, all you need to do is say apply sigma inverse and then apply the key and then apply sigma inverse and apply the key, et cetera, to kind of unwind these applications of sigma and your secret key, right? So it's very easy. If you know the key, then it's very easy to decrypt. But on the other hand, it's very hard to invert this encryption if you're mistaken on even a single bit of the key. So let's say that you tried to decrypt a message with a guess of the secret key, but you happen to guess wrong on the secret key. Like let's say you got a single bit incorrect in your guess of the key. Well, the intuition is that because of the scrambling nature of this permutation, that error that you made in the key would kind of spread or infect all of the different bits of your decrypted message, such that if you tried to decrypt your encryption with, and got the secret key, even wrong on one bit, your attempted decryption would give you complete garbage, right? So, and that's coming from the fact that this permutation sigma is highly scrambling. And it's the same intuition that tells you could reuse the same key for many different messages, because essentially each message gets mapped to essentially a completely random string that has essentially no information about the message. And it turns out that you can prove security of these sorts of block ciphers in some model where you assume that this permutation is totally unstructured. And this is actually, this kind of intuition is at the core of a lot of modern crypto systems. Okay, so why did I go through all of this detail to explain how block ciphers work? Well, it turns out that this theory of block ciphers is intricately connected to quantum gravity, and that's one of the main results of our paper. So in particular, if you look at these scrambling states, these shock states that are being considered in the context of the wormhole growth paradox, they are states of the form, you have some reference state and you alternate between applying scrambling operations and local operator insertions. If you just compare these to the formula for a block cipher, you can see they actually look extremely similar to one another. So the application of the secret key is analogous to the insertion of a local operator. And the application of the scrambling evolution, e to the IHT scramble in the CFT is analogous to the application of a fixed but highly scrambling permutation sigma. So the main connection that we've made in our work is that these shock states that are being considered in AdS CFT are actually the quantum analog of a block cipher. So I'm calling this tongue-in-cheek a block cipher with BLOCH, after Immanuel Bloch. But the basic idea is that they're kind of almost directly the quantum analog of what a classical block cipher is. Now, the reason we care about this is it turns out that for both quantum block ciphers and classical block ciphers, that there's a well-known way to turn a block cipher into something called a computational pseudorandomness construction. So what is computational pseudorandomness? Well, in the context of quantum computing, a collection of efficiently preparable states is called pseudorandom if these states are kind of computationally indistinguishable from hard random states. The details of this definition end up not being incredibly important for our work, but the basic intuition here is that a computationally pseudo-random state ensemble is something that looks a lot like a unitary T design, but it has computational security properties instead of information theoretic security properties, right? So T design says that T copies of the state are information theoretically indistinguishable from a random state. Saying that a state is a computational pseudo-random state ensemble is saying that even though they might be information theoretically distinguishable from hard random states, from a practical standpoint, they are not distinguishable by efficient quantum computations. And our main result is to argue that these shock states that are being considered are naturally form a quantum pseudo-random state ensemble because they're kind of the direct analog of quantum block ciphers. In particular, what we do is we prove the pseudo-randomness of these states in kind of a natural black box model where we assume the scrambling evolution of our unitary is totally unstructured. And then we conjecture that the same pseudo-randomness properties holds when you consider the true evolution by the CFT Hamiltonian. And unfortunately, I don't have time to go into the details of this proof sketch, but I have a few slides later on. If people are interested, I'm happy to discuss this more, maybe in the questions, if we have some more time. I'm going to skip the details of this proof. So let me jump straight to what the implications of this pseudo-randomness statement are, and then we'll discuss the interpretation. So what our argument says is we're arguing that you cannot efficiently tell shock states apart from one another, even though they correspond to very different lengths of time evolution and therefore correspond to very different wormhole volumes. So what this means is immediately corollary is that the complexity of these shock states, or more generally, the length of time that they've been evolving, is something that's not feelable. So to put it another way, let's say I considered creating shock states where I time evolved them for total length n cubed, where n is the entropy of the black hole, and consider another ensemble of shock states where I time evolved them for total length n to the fourth. Then what our argument would say is that there is no quantum algorithm that can distinguish these two ensemble of states efficiently. And what that immediately implies is that there's no efficient quantum algorithm to estimate the complexity of these states. In other words, to tell me, what's the complexity high, like n to the fourth, or was it low, like n cubed? That immediately implies there's no even very coarse estimate to the complexity of the CFT state. So what this immediately means is that, because of this wormhole growth paradox, there has to be some quantity that's the dual to volume. But what our argument is saying is kind of whatever that quantity is, whether it be circuit complexity of the CFT state or any other quantity, it has to be something that is exponentially difficult to compute with a quantum computer. So in some sense, this is saying that this discomfort that we're feeling as complexity theorists with this conjecture is somehow inevitable. So there's not some other quantity you could have picked on the CFT side to be the dual that doesn't have this property. So whatever quantity is the dual to volume has to be something like complexity. It has to be something that's not feelable. On the other hand, we argued that the wormhole volume of the corresponding AdS states is something that is actually easy to compute. In particular, we did this by giving an efficient algorithm which achieves a very rough approximation of the wormhole volume of the corresponding AdS state. So this is saying that kind of the volume side of these complexity equal volume like conjecture is easy to estimate. Now, the details of this algorithm depend a bit on exactly what you believe, what information you believe is easily extractable in AdS CFT from the CFT state. So they're kind of, we kind of wrote both of these arguments in our paper, and I would love to have further discussions with quantum gravity people about which of these is kind of the best assumption. But if you assume that somehow this AdS CFT dictionary allows you to extract the global metric of the AdS state from the CFT state, then I think it should be clear that computing the volume of the corresponding wormhole is something that should be manifestly easy to do. Like this is saying, if you had a computer simulation of GR where you just stored some discretization of the metric, computing the volume of a wormhole is something that's relatively easy, particularly because all of the metrics we're talking about are just kind of the standard AdS wormhole plus some kind of very small perturbations thereof. But on the other hand, one might also take a more kind of restrictive picture of AdS CFT. If you kind of are a proponent of kind of a very strong form of complementarity, then you might believe that the AdS CFT dictionary doesn't allow you to extract the global metric of the AdS state, but maybe it might only allow you to reconstruct the experiences of individual observers living in the AdS space. So maybe there isn't one coherent picture of the kind of quantum gravity state, but maybe you can only produce these kind of local descriptions of what the gravity side should look like. But we argue that even in this model, it should be algorithmically simple to extract the wormhole volume of the state by basically considering simple experiments where you say throw polynomially many observers into the wormhole who can either meet pairwise and exchange information or not, depending how close they are or whether or not they're separated by a horizon or something like this. And we argue that by some kind of general argument like this, even though no single one of these observers can measure the wormhole volume, there is some sense in which they collectively compute the wormhole volume, in the sense that if you could simulate what happened to each observer and then post-process the outcomes of these experiments classically, then to say count up how many of them managed to meet or which ones of them managed to communicate, we're not separated by horizons, then post-processing these experimental outcomes would give one kind of a very coarse approximation to the volume. And even though this is not an experiment that's physically realizable, because these observers couldn't in real life all talk to one another before hitting the singularity, in a computer science sense, it would still be an efficient algorithm for computing this quantity, and that's kind of all we need to get some of this tension with the fact that the complexity is something that's hard to compute. Okay, so from this, I think we now should be able to easily see, why our argument is pointing to this statement that the dictionary should be exponentially complex. Because what we've argued in this talk is, okay, in AdS CFT, there's this wormhole growth paradox. There has to be some quantity on the right-hand side that is the dual to volume. Whatever this quantity is, it has to be difficult to compute. It has to be something like complexity. That's kind of our first result based on the pseudo-randomness construction. Now, our second result is that the wormhole volume is something that should be easy to compute on the AdS side. Well, this means that this AdS CFT dictionary should be transforming a problem that's difficult to compute with one that's easy to compute. Well, that immediately means that the dictionary itself has to be exponentially difficult to compute. In complexity theory, it's for the same reason that you can't reduce a hard computational problem to an easy problem. If you've done that, unless p equals np or something, it usually means you accidentally made your reduction between the problems kind of exponentially powerful. That's kind of the exact same argument that we're making here. Now, I saw a raised hand, so feel free to chime in with a question.
Yeah, I have a question.
Yeah, sure.
So you said that you can, you can compute the volume of this wormhole by gathering the information of each observer in the interior before hitting the singularity.
Yeah.
But I mean that which volume of this wormhole that are these observer computing? Okay, so starting from some time slice and then consider observers on the time slice.
Yes.
Then so they start exchanging their information.
Yeah, I'm thinking.
But during this exchange of information, the time is passing, so that the volume of the wormhole is changing. And so I'm wondering, are they computing the volume of wormhole of the initial slice or the of the final slice?
Oh yeah, that's a good question. I'd say of the initial slice is probably the most reasonable one, but the amount of their proper time that elapses in this experiment is, I think, really small, right? So I think they all hit the singularity in something like LADS timescale or something like this, right? So I don't think it matters too much if they're estimating the initial or the final, because our argument ends up being that it's really hard to get even a very, very coarse approximation to this volume. So it doesn't really matter the details of which, if you're computing at time slice t or t plus epsilon, it kind of it kind of doesn't matter in the argument.
Okay, I see. Thanks.
Yeah, no, that's a good question. Thanks. Yeah, great. So I was saying, so this is what this argument is pointing to is that somehow this dictionary looks like something that should be exponentially difficult to compute. You could use this to argue, maybe this means this AdS CFT dictionary is something that will be permanently under construction. In other words, we know in AdS CFT that there are certain states are dual to other particular states, but like we can always compute particular examples of states that are dual to one another, but kind of making this a very simple or general theory to be able to compute this duality and move across these two different theories is something that might be in general something that's very difficult to perform. So I think there are a lot of interesting questions for how to interpret this result in terms of what does this mean for AdS CFT. I'd say that there, maybe to caricature it, there are kind of two different perspectives one might take on what this result means. So the first result is one might view this high complexity of the dictionary as a bug in the theory. One might view it as something negative that maybe was not expected in AdS CFT. And the reason one might view it this way is, you could worry that it could limit what one might be able to learn about wormhole interiors by studying CFT states. Like, in particular, our argument is arguing it's very hard to reconstruct wormhole interiors from CFT states. That's kind of the region of space-time from which our contradiction is being kind of derived. And so you could see this exponential complexity of the dictionary in this regime as arguing that, it might be very difficult to learn about what happens in quantum gravity on the interior of wormholes. In fact, Susskind even recently suggested that this could be kind of a more general phenomena. He proposed that maybe we're seeing something like a computational form of the cosmic censorship conjecture, where maybe all of these exponentially complex dictionaries or violations of quantum extended Church-Turing thesis are all phenomena that are shielded by horizons, much in the same way that Penrose, conjectured that all singularities in GR are something that have to be shielded by horizons, of certain forms. So yeah, anyways, I think that's kind of one interesting perspective one can take on interpreting this result. There's also the possibility that one might be able to view this high complexity of the dictionary as a feature of AdS CFT. Maybe it actually is playing a positive role in the correspondence. So there was a very nice paper of Kim, Preskill, and Tang recently, who argued that there are, in some settings, particularly related to kind of one-sided black holes, that computational pseudorandomness might play a role in a form of computational protection of causality. So in particular, they were considering a system in which, in a one-side black hole, where the old Hawking radiation is somehow dual to the black hole interior. So in principle, someone could manipulate the interior acausally by manipulating the old Hawking radiation. But they argued that if pseudorandomness is present in this system, that this means that any of this kind of acausal long-distance manipulation of the interior is something that would require high complexity and would therefore be something that is prohibitively difficult to do from a practical standpoint. So this is kind of some similar in view to kind of older arguments of Hayden and Harlow and others. So I think this is also an interesting proposal because it's saying, maybe this high complexity of the dictionary could be playing a positive role. And finally, I'll note that there's kind of one other way that I finally note there is another way of avoiding the consequence of a high complexity dictionary in our arguments, which is that it could be that the dictionary is of low complexity, but the quantum extended Church-Turing thesis is false in quantum gravity. In other words, it might be that even if the dictionary is easy to compute, that the dynamics of what happens on the interior of an AdS wormhole is something that is exponentially difficult to simulate, even for a quantum computer. And I think that would be kind of a very surprising conclusion, but I think it's an interesting thing to warrant further investigation as kind of to what extent, what one thinks that all of these aspects of quantum gravity are things that should be efficiently simulable with quantum computers. And with that, that's the end of my talk, and I'm happy to take questions with the remaining time.
Thank you very much, Adam, for your nice talk. So any
Great, thanks. Yeah, I see Tadashi has raised his hand.
Hi, thank you very much. Very illuminating and very interesting talk. So I have a question about the interpretation of your results. And so in AdS CFT, we can calculate like complexity by computing volume. But actually, we are using some so-called large n limit. N is the size of degree of freedom, and or more exactly, is the kind of rank of gauge group, but it's kind of degree of freedom of the quantum memory system. And in the leading limit, n goes to infinity, we can calculate many quantities classically, like volume or entropy, area, and complexity. But if we try to calculate 1 over n next order calculation, then we really need quantum calculation. I expect also complex case, we need a really quantum complexity. And it's quite hard, I guess, according to your, I think, talk. So do you think this kind of hierarchy, changes, saves the story? Or, we can easily calculate leading term, but this next term is very, very difficult. This kind of structure is related. Is this related to your story of pseudorandomness, or that's I'm very curious about.
Oh yeah, that's a really great question. So okay, first I think it's very interesting to ask if the higher order questions are how easy or hard they are to compute. I think that's a very interesting question, maybe in its own right. I'm not sure that this would change the story though, simply because our pseudorandomness argument ends up telling you that the volume is something that's hard even to estimate coarsely. And if you're estimating the volume very coarsely, presumably you could discard the 1 over n corrections terms, right? Because you would kind of only need leading order terms in that calculation. So it's saying somehow, so Yeah, so I think it's identifying that, you know, because you're saying that you have a way of computing volume, right? You know, up to these small corrections, you have a good way of approximating volume. It's saying that something else is what's being difficult in the theory. And the thing that I think is implicitly being assumed is that, you know, you're assuming that for the CFT state, you already know the metric. And therefore, once you know the metric, then you can compute the volume, right? Is that correct? Or is this?
Yeah.
Because the dictionary that we're arguing is complex is kind of a one-size-fits-all dictionary. Like if you didn't know, like, okay, if you have a particular CFT state in mind, like the thermofield double evolved for time t, then of course you could know already what the dual is and therefore compute the volume and perform those integrals, and it would not be something that's difficult. Okay, what we're saying is hard is that if you want to have a map that given an unknown CFT state, like I give you a physical copy of that unknown CFT state, say many copies of it, but I don't tell you which one I gave you. And I want you to physically extract for me the metric from that state. And then from the metric, you can compute the volume. That extraction of the metric from the state is what's very hard. It's almost like a physical thing. Like if I handed you a physical copy of the CFT state, if I didn't tell you which one it was, then that should be hard. And that's different than giving you an analytical description of the CFT.
So you are suggesting that even leading contribution is very difficult to calculate.
Yes, or
it's very complex.
It's very difficult to extract the metric.
But also metric
from an unknown CFT state.
Metric can be extracted from also entropy. And do you think entropy or entanglement entropy or also even black hole entropy is easier to estimate?
Interesting. You know, my general thought, you know, I usually think of entropy as being a quantity that's very difficult to estimate for quantum states. Like it usually ends up being like QSCK complete or something like this. The various entropy or NIQSCK complete. It's yeah. So my initial guess would be that the entropy that you're wishing to estimate that could be a correlate. Maybe it's something that could be hard. But yeah, that's an interesting question. So
thank you very much.
Yeah. Thanks. Yeah, those are great questions.
Any other question or comment? So I have one question about the construction of pseudorandom state. So I think already in the paper by JFNG et al. Constructed one example of pseudorandom state from pseudorandom function. And in your construction, what is a different point from their construction?
Yes. So what's different from our construction is that we're not basing it on one-way functions. We're basing it on the same cryptographic arguments that are used to prove security of block ciphers, which is like basically a random oracle model proof of security. So yeah, I think the way to view it is instead of saying we have pseudo-random states conjectured by one-way functions, we have pseudo-random states in some kind of classical random oracle model or something like this. And somehow that so it's kind of a different type of evidence for pseudo-random states, but by making that switch, it allows us to construct pseudo-random states from this very natural subset of states that were already studied in the context of AdS CFT. So the whole point of our constructions was we were trying to show, you know, something like JLS already identified, we could manifest even in these tiny subset of states. So I'd view it as like a second and like a custom pseudo-randomness assumption that was custom tailored to the physics of the system that we were talking about. But of course, if you JLS was saying more, if you have a universal quantum computer, then using very artificially engineered sorts of states, then one can create these states. And this is saying they're somehow a little more generic than that.
Do you have any restriction on the gate set that you can use? You can basically use any universal gate set in your some CFT time evolution plus shock.
Yeah, I don't think the choice of the shock gates will matter very much. But the choice of the scrambling operator, we proved the security in like a black box Oracle model where we model the scrambling operator as a unitary U, and all you can apply is black box U or black box U inverse. And we prove, we sketch an argument that you need to take exponentially many queries to U to break the construction. And then we're just conjecturing that that same black box security still holds in the white box model when you know what U is, right? I think there are a lot of details left to be kind of flushed out there in terms of to what extent that security holds in the white box model. Some of the very naive things you might hope to say actually are false in the white box model. We wrote a section of this in our paper about this, but we think there are kind of some more modifications to our construction that would still maintain security and pseudorandomness even against these things that make use of kind of more structure in the CFT Hamiltonian.
Okay, thank you.
But I don't know about gate set in particular. Like in the black box model, all we use is when you apply a shock operator to a Haar random state, it renders it nearly orthogonal to itself. I think that's a property that holds of a lot of different quantum gates one could pick, right? As long as it's a big rotation and not a very small rotation.
Okay. So there is one question. Please, Ibura Akaru, please.
Yeah, thanks a lot for the great talk. So I have a question. So you mentioned some comment on your slides before. So you mentioned that the dictionary only allows reconstruction of experiences of individual observers.
This is one way of viewing it, though we have talked with other people who have said, well, maybe the right way to view it is that maybe we're just really assuming you can extract the metric, so maybe you don't even need this picture. But yeah, sorry, continue.
So I just wanted to ask what you exactly mean by this. I mean, but yeah.
Yeah, I'm not entirely sure, even myself, but I think we were more trying to consider a more general model where if you have an observer in the AdS and you have a CFT state, then you could say reconstruct the causal patch of that observer or something like that, right? That's different than being able to say you could reconstruct the whole space-time.
I see. Yeah, because I'm thinking, because I mean, what you're talking about is especially the dictionary in the large n limit. So it's a semi-classical limit. So from that perspective, it's not so surprising that this might be working in some sense.
Oh, that what might? Oh, you mean that you might be able to get the entire metric?
Yeah, yeah.
Oh, I see. Yes. Because it's semi-classical, so it's the other side is just PR.
You just I mean, consider the dictionary in a certain limit.
Oh, okay. Yeah. That's reasonable. Yeah, it could be that this whole thing of considering different observers might be a red herring, and maybe we should just be considering this model where, because it's semi-classical, you should just be able to get the whole metric.
Okay.
Yeah, that's a good
thing.
And if you make that simplifying assumption, it ends up simplifying our statements. Like if you just say by the dictionary, what I mean is given an unknown CFT state, extract the global metric, we're showing that task is hard. Even though for particular states, you can know the metric, right?
Yes.
So it's saying somehow the more generic task of metric extraction is hard when you don't have the analytical description of your state, but just physical copies of it.
I see. Great, thanks a lot.
Great, yeah, thanks.
Okay, any Ugajin-san, please.
So can you comment on the existence of the firewall in the black hole interior? For example, if I start from generic CFT states, I mean, what people expect is that it doesn't have a smooth, the geometric dual, but instead, it has, smooth geometry outside of the horizon exterior, but interior we run into some firewall, and so we don't expect smooth, that geometric dual in the interior. And so what do you find related to this? That the existence of firewall?
Yeah, that's an interesting question. Yeah, so we never actually consider that in our paper because we're only considering the duals of shock states, right? Which are kind of simpler, like they're kind of designed because there's perturbations. They have smooth gravity, or they have reasonable gravity. Yeah, so I'm not sure if our arguments directly say anything about generic ones. Yeah, that's an interesting question.
I see. Thanks.
Any other question or comment? So you mentioned that generalized quantum Church-Turing thesis could be wrong. But so if this is if in that case, do you think which type of complexity class we can solve by using this new physics machine, like PP or
Oh, interesting. Yeah, that's a good question. Yeah, I actually don't know. If it allowed you, it would be something that would allow you to break pseudo-random state ensembles. So like NP, at least QMA or something would allow you to do this. So there is an upper bound on how powerful it would have to be. But yeah, that's an interesting question. I haven't pinned down exactly what class that would be.
Okay.
Yeah.
Thank you. So Numasawa-san, please.
So I think so. You said so. You give some formula to roughly estimate the complexity. But so how rough is it? For example, so can you say something like a coefficient in front of the volume in gravity side?
Yeah, I'd say it's hard to estimate up to a polynomial factor. So determining if it's the complexity is less than n squared or more than n to the 100 or something like this. That even that course, as promised, one of the other is the case. Even that is hard. Yeah. So even like pseudo-randomness gives you actually very strong properties, because remember, pseudo-randomness is saying it's hard to distinguish these states of very low complexity from Haar-random states, right? Haar-random states have exponential complexity. So it's saying it's hard to tell states that are really, really complex from states that are very simple. So even very, very coarse estimates end up being hard.
I see. Okay, thank you.
Yeah. So exactly. So it's kind of, it's a little counterintuitive, because normally when one thinks of physical quantities, one thinks like, oh, the approximation is easy, but maybe exact computation is very hard. But complexity is a very different quantity. Even the very coarse approximation is already typically very hard.
I just want to confirm. So which part can you estimate? Some exponential part?
The argument is you cannot estimate.
You cannot estimate. I see.
But so like the argument goes something like this. Okay, of the CFT states, we cannot estimate the volume. We cannot estimate the complexity or anything like it. But if we had a dictionary that were efficient, we could take the CFT state, extract the metric from it, and compute the volume. That would be a coarse estimate of the complexity, right? But if we know that coarse estimate is hard, then this something has to be of exponential complexity along this path, right? So that in particular means the dictionary has to have been exponentially hard to compute. So the argument is like the volume is easy to compute to that much approximation, but the complexity is hard to compute to that much approximation.
So you mean that it is very hard to estimate the metric?
Our argument is about complexity being hard to estimate, but that implies that given the state, it has to be hard to extract the metric, because otherwise you could extract the metric easily. compute the volume would be an estimate complexity.
I see. Given the metrics, then it is easy to compute volume. So it the estimating.
If you had the metric, it should be easy because these are just wormholes with tiny perturbations. That's it.
I see. Okay. Thank you.
Yeah. Thanks.
Okay. Any other question or comment? Okay. Takayanagi-san, please.
This is related to also Ibrahim's question and related to my also previous question. But so in AdS CFT, so we are you also assuming this classical gravity description, and that means we are restricting particular class of quantum states, which we call some holographic states.
Yes.
And maybe this constraint also gives us some hint where by using this hint, maybe it's easier to extract a complexity.
So that's why. Okay, so I don't think that's possible, and the reason is that the shock states we chose are exactly states that do have smooth gravity duals, right?
Yeah.
So we're showing even for those states, it's hard to estimate the complexity.
Yeah, but I'm not sure, but what I thinking just maybe there are some extra hint. Because we are restricting particular class of quantum state and using this hint and combined with this algorithm to calculate complexity, maybe it's easier to estimate it.
Okay. Yeah, that's interesting. But I think our arguments are still saying that it's hard to estimate them because we're saying, that like even for states obeying this hint, let's say you have a hint, it has a it has a smooth gravity dual. That means it has these simplified entanglement properties and all these, it obeys Ryu Takinagi, obeys many of these things. Even for those states, it's still hard to estimate.
Yeah,
because even those states allow pseudorandomness.
I see.
So maybe I might be misunderstanding your question though.
Yeah, because the generic quantum state in CFT is like some quite many superposition of holographic state, which is very quantum, and it's kind of superposition of quantum space-time. And in that case, it's very we can expect the estimation volume also very hard.
Yes.
So that's a kind of but if we restrict only particular class of quantum state, like holographic state, we just have a classical gravity dual. To me, this is a very strong kind of restriction of quantum state.
Yes. But the interesting part of our argument is that even those states, with that strong restriction, it's still hard to estimate their complexity.
I see.
Still arise in the subset. So that's kind of why we went to kind of great lengths to try to put the pseudo-randomness into this very tiny subset of states, because we said, okay, we only want to study states that have smooth gravity duals. They have the simplified entanglement structure. They have lots of things. Even for those, it's still hard. So unfortunately, that's like not enough structure to do that. There is an interesting question. Can you add more structure to then make it easy? I think that is still open. If there's further structure that somehow doesn't allow these shock states, then it could be possible that some of those it's easier to estimate complexity. Like for example, if you remove the shocks and you just have time evolution forward and backwards, then it is easy to estimate complexity because all you need to do is take your state and time evolve backwards until you hit the thermofield double, and then do a swap test with the thermofield double, right? So that's like too small of a subset of states. There it's easy. We're showing these shock states, it's hard to estimate complexity. But yeah, there's great questions of what other subsets of states still have this property that it's hard to estimate complexity.
I see. Thank you very much. Yeah,
thanks.
Any other question or comment?
Okay, great. Well, yeah, thank you very much for having me. I really enjoyed the discussion.
Okay, thank you very much for great talk.
Thanks.
Okay, so we have 3 minutes break, or should we take more break? Is it okay? Okay, so let's take 3 minutes break, and then the next speaker will start from 10:15. Okay,
Great.
thank you.
Thanks.
Thank you. Next speaker, could you check the slide representation?
Right, I do.
Okay.
Just a moment.